Part 4. We've talked already about climate scenarios, but then what do we do with them and how do they turn into climate projections? We also talked about this curve in the road and how we need to take our eyes off the rearview mirror, which we've been using for pretty much all of our planning as long as there's been human civilization on this planet, and look ahead at the curve that we're already on, our wheels already on the rumble strip, to see how steep it is and how we can make it around safely. There's two factors that determine how quickly this curve is approaching us and how steep it is. The first is what we just talked about, scenarios, human decisions, and the second is this: how is the climate system responding to the unprecedented experiment that we are conducting with it? And it truly is unprecedented. According to paleoclimate records, as far back as we can go, the closest analog to what we're seeing now, which was over 55 million years ago, there was about 1/10 the amount of carbon going into the atmosphere due to natural factors at that time, as we humans are putting into the atmosphere today. So it really is unprecedented, and that's why there's some uncertainty regarding how the climate system is going to respond. So how do we figure out what the future looks like? Well, there's three basic options. Option number one, crystal balls. They do not work so well, though. You won't see a lot of those in climate scientist labs. Option number two, which people often assume we use, I run into this a lot on social media, people assume we just use statistics. You say, temperature's going up, draw a straight line through it with an arrow at the end. Or maybe just do a correlation with carbon dioxide. And of course, I don't know if you know, but there's these wonderful websites where they do correlations between things like, Nicolas Cage movies and people drowning in swimming pools and the number of pirates and global temperature. And you can create spurious correlations with a lot of different interesting things. But our climate models and the information we use to project the future are not based on correlations, even though this correlation between global temperature and carbon dioxide looks pretty good. Why? Because we understand the physics. We actually understand the specific wavelengths at which the vibrational and rotational bands of the molecule of carbon dioxide and methane and other heat-trapping gases actually absorb and re-emit radiation. We've understood those since the work of Joseph Tyndall in the 1850s. And because of that, we have understood that when these gases increase, global temperature also increases because it's as if we're wrapping an extra blanket around the planet. And we've known that since the work of Eunice Foote in the 1850s as well. So statistics do show us a nice correlation between global temperature and carbon dioxide, but we have understood the physics, the reason why there's a correlation, for over 150 years, actually over 170 years now, and that is the information we use. Why? Because when you look at these correlations, they break down when you start to go down to finer and finer scales. If you look at US temperature versus carbon dioxide, you only have a correlation of 0.5. If you look at the correlation for Texas alone, where I live, you're down to 0.46. And if you started to look at the correlation between heat waves or heavy precipitation, and at a much smaller scale, that of a watershed or a city or a county, the correlation would be even poorer. Why is that? It's because the climate system is complex. But even though it's complex, it obeys specific physical rules and laws, many of which we've known for a very long time, and all of which are as applicable on Earth as they are on any other planet, in fact, on the opposite side of the universe as well. It's physics. So that's why option 3 for generating climate projections is physics, and that is the one that we use. Specifically, climate models are made up of hundreds of mathematical equations that represent different parts of the climate system, number one, and number two, how those different parts interact with each other, how they exchange heat, momentum, moisture, and more. So the climate system consists of the biosphere, the ocean, the hydrosphere, the cryosphere, the atmosphere, and then the lithosphere. And what the climate models do is they not only include all those different systems, but they model how things move between the systems. Like, for example, when ice melts, the water goes from the cryosphere, which is frozen, to the hydrosphere. When the water evaporates, it goes from the hydrosphere into the atmosphere. And then when it condenses and falls back out again, if it's over the ocean, it goes into the ocean. So that's what climate models simulate. Now, it can get complicated really quickly, and this is, and I do not mean to be sarcastic here, this actually is a simple diagram of the physics in a climate model. Simple because it only contains a few of the processes primarily related to energy and radiation. It is complicated. Climate models take weeks to months to run on the most powerful supercomputers that we have. They're thousands of lines of code long. But they are not based on crystal balls. They are not based on simple, naive correlations. They are based on very basic and fundamental physics and increasingly chemistry and biology, some of which we're just learning today, but some of which, the very basics of which, we've known for a very long time. In fact, as you can see here, the very first climate model was calculated by a man called Svante Arrhenius back in the 1890s. He was able to calculate how much the world would warm if we increased levels of CO2 in the atmosphere, and he even calculated how much more the Arctic would warm than the rest of the planet. Over the years, we've added more components: the hydrological cycle, nonlinear fluid dynamics, sea ice, land surface chemistry, vegetation, biogeochemical cycles, and carbon. We've added more components or pieces to the climate models, so they become more and more complex. But they still find pretty much the same thing Arrhenius found, which is the more heat-trapping gases you add to the atmosphere, the faster it warms, the greater the impacts, and the Arctic warms faster than the rest of the planet. We'll talk a little bit more about why that is when we get to the feedbacks. But first of all, I want to give you a visual of what a climate model looks like, because it's sometimes helpful to actually think about it this way visually. So you take the whole planet. We've got land surface, we've got atmosphere, and we've got ocean. What a climate model does is it divides that into smaller and smaller grids. The more powerful the computer, the finer the grids we can use. The finer the grids we can use, the more physics and chemistry and biology we can resolve. Resolution isn't everything, but it definitely does help. This is what allows us to actually experiment with the planet, because I don't know if you've ever thought about this before, but climate scientists can't put what they study in the lab. They can't experiment on it. So instead, we use the models to experiment on. That is our lab. And it's so funny whenever anybody asks to see my lab, because my lab is the supercomputing center. So in some cases, they've actually literally taken pictures of me in the supercomputing center, even though I always connect remotely anyways, because that's the only visual that I have for my lab. So that's why we use these thousands of lines of code on some of the most powerful supercomputers in the world, because that is our lab to test out different future scenarios, as well as to apply the climate models to different planets. Yeah, they can be applied to different planets. They have hurricanes on Jupiter that you can study with climate models because it's the same physics. We can apply them to Earth in the distant past. We can look at what's already happened over the historical record. We can compare them with observations. But climate models are very valuable because not only do they help us understand the climate system, but that is what gives us our projections. And why do we need projections? We need them because our road is hitting a massive curve. That curve is entirely due to us. We humans are the reason the planet is warming today. It is changing at an increasingly rapid pace in ways that can't be predicted by looking in a rearview mirror. For the first time, it's not the sun, it's not natural cycles, it's not volcanoes. We are in the driver's seat. Not only that, but in the future, the conditions that we are going to experience, even in our lifetimes, let alone those of our children, are likely to far exceed the range of natural variability to which our environment is accustomed. So we need to know what's happening because and by our here I mean every living thing on this planet, our future is at stake.